probability unit is, for the most part, about determining odds, trying to find out how likely things are. And that's where you're going to be spending most of your time. But another big section, or kind of a related topic to probability, is the idea of set theory. And set theory, you've actually been using sets a couple of times through the year, and maybe you haven't really realized it. What a set is a list of things. Mathematically, they're going to be numbers. And often this set has something in common. But the way that we mark a set is with these curly brackets. These curly brackets here indicate that there is a set. So if we have curly bracket, and then, I don't know, 2, 3, 5, 7, 11, then we have a set that contains the elements 2, 3, 5, 7, and 11. Element, that's another important word there. Element is a member of a set. A member of a set. And there's a notation for this. An element is this, it's not actually an E, but it kind of looks like one, but this notation here. You'll see this again later on in a different video, but this notation here refers to an element. So if I say that X, if you see something like this, written like this is read as X is an element of the set A. So if this is the set A, then 2, 3, 5, 7, and 11 are all elements of set A. They're all single items found in set A. This isn't the only kind of set, though. I mean, this is a set of integers. These are all whole numbers here. These are all positive whole numbers at that. You've been using sets in other circumstances as well. Whenever you do interval notation, if you remember that. Back from probably the inequalities unit. Probably you haven't used interval notation since then. But if you remember this, we had things like with parentheses or with the squared off brackets. And so the parentheses would mean, I don't know, to do like 2 comma 11 and then 2 comma 11. The way that we read this is all real numbers between 2 and 11. So it includes the integers 2, 3, 4, 5, 6, all the way up to 11. But it also includes the decimals between them, 2.5, 7.7, pi, for example, is in that interval. The notation for this, though, would be 2 is less than x is less than 11, the inequality notation. Because the thing is, this is what we call an exclusive interval. Because what we're doing is we're saying, I want everything between 2 and 11, but not 2 and not 11. I want to have everything between 2 and 11, but not 2 and 11 themselves. You remember the way we graph this. We have a 2 down there, we have an 11 over here, open circle on both the 2 and the 11, and then shading in between them. Whereas this version, with the square brackets, that means we have 2 is less than or equal to x is less than or equal to 11. And so we call this an inclusive interval. And so the corresponding graph for this, as you should remember from the inequalities unit, we have 2, 11, and we have a filled-in circle on both of these things, to show that not only do we want everything between 2 and 11, but we want to include 2 and 11 themselves. The big difference between writing a set using interval notation and using a set using this style notation is that for the interval notation, we mean all real numbers, all of the whole numbers, all of the fractions, all of the decimals, everything. Whereas here, this is just this list. Just these 5 numbers. Only these 5. Not 4, not 4.5, not pi. They're not in this set. So when you see the curly bracket notation, you got to make sure that you're keeping in mind that it's only the things that are written there that are a part of that set. Whereas for the interval notation, then it could be these two numbers and then everything between them as well. Now, there does exist a set that doesn't have anything in it. I mean, think of an empty box. There's a box, the box exists, but it doesn't contain anything. And so we call that the empty set. The empty set, it's exactly what it sounds like. It is a set with nothing in it. And so there's two ways that we could denote the empty set. We could have the set of brackets with nothing in it. I mean, there's a set. There's nothing in that set, so that's the empty set. But another way is a circle with a big slash through it. And so the empty set is just saying that there's nothing in this set. There's nothing, this set exists, but there's nothing in it. So don't put curly brackets around this. This is not the right notation. We have either the brackets with nothing in them, or we have the circle with a slash through it. But don't put brackets over the circle with a slash like that, because what you've essentially done is now you've created a set that contains the empty set. Think of putting an empty box inside of a box inside of a bigger box. You got two boxes. The first box, the big box, has something in it. It has a box in it. The smaller box has nothing in it. So it's not quite the same thing. It's a little bit confusing. Just don't worry about that. Just either go with one or the other of these. Some other special notation that comes up when talking about sets is when we're talking about big sets of numbers, big groups of numbers. In fact, I've mentioned the two important ones already earlier when we were talking about the difference between this style of notation and the interval notation. When we have these numbers, these are all integers. And so if I wanted to describe the set of all integers, I use the letter Z. But not just a Z, I have to use a Z with kind of a weird double thing right there. So this is the set of all integers. Positive, negative, and zero. So this would be, negative, coming in from negative infinity, then we get, negative 3, negative 2, negative 1, 0, then 1, 2, 3, 4, and so on to positive infinity. It's an infinitely big set. Goes on forever in both directions. But it's a set that contains all of the integers. The Z here has to do, why this is the letter Z, is because the German word for integer, which unfortunately I can't remember right now, so you'll have to look this up. The German word for integer begins with a Z. And so the first mathematicians who kind of started using this notation were German, and so they used this notation. Similar to this, then, is the R. The R with the double vertical bars there. You may have used this in your class already, this notation here already. You might also already remember that this is the set of all real numbers. The set of all real numbers. Or just simply all real numbers. So again, this includes all of the integers, plus all of the rational numbers, plus all of the irrational numbers, like pi, like the square root of 2, things like that. Positive and negative numbers as well. This is basically all the numbers you've ever worked with so far. There do exist other numbers, and you'll get into them a little bit later on in your math career. The last thing to mention about sets is how they relate to each other, or how they can be combined. And we'll get into this in more detail in a later video, but the primary two ways that we combine sets is by looking for an intersection and a union. So an intersection is an overlap. It's what the two sets have in common. What the two sets have in common. So think of standing at the intersection of Cayuga Street and Buffalo Street, for example, right there on the edge of the Commons. If you're standing in the middle of that intersection, you're technically on both streets at the same time. You're on both Buffalo Street and Cayuga Street. So the intersection is the overlap. If you remember learning about Venn diagrams in a previous class, you know, we had A and B. The intersection would be this stuff in the middle. So exactly how we find intersections, again, check out the third video for that. But for now, the only other thing we need to remember is that the notation for the intersection is an arch shape. So we have A and then intersection B. And the convenient way of thinking of this is that an intersection really means and. And so if you think here, this kind of looks, especially if I draw a line across it, it looks like an A. So the arch means and, means intersection. So we have that. This isn't actually part of the notation, keep in mind. It's just a way to perhaps remember it. All right, fix that. Now, the union, on the other hand, is basically everything pooled together. Both sets, or more if there's more than two, both sets pooled together. So it's the or, in a way. It's the thing that it's the set that contains everything that appears in either set. The intersection is the things that only appear in both. The overlap, the union, it could appear in one, it could appear in the other, it could appear in both. It would be everything. Again, this makes more sense with examples, so check out the examples in the next video, or the third video rather. But again, the notation that you need to know for this is, this might not be a terribly huge surprise if the intersection is an arch shape like this. The union, which is kind of like the opposite of the intersection, is a U shape. This isn't actually a U. It's just this kind of dipping down shape here. And you can remember this by just, if you imagine kind of linking it on top again, you get sort of an O. And so we get or. The A or B would be the union of the sets A and B. The intersection of A and B are what appears in both, the overlap between A and B. So that's all of the notation and definitions and terms that are a part of this unit. There's going to be a lot of terms in this unit as a whole, both in the honors version and the non-honors version. So hopefully you can try to keep track of all these things. But this will hopefully at least be a good place to start.